This is part 7 of topic 2 in atomic bonding. So now let's return to our application of aircraft wings. Remember that in order to have a good aircraft wing, we want to maximize the elastic modulus and minimize the density rho. In fact, we can actually create a property called M, the specific modulus, which is equal to E over the rho, the density. If I plot Young's modulus versus density, and I say I want a specific value for M, any material that lies on this line is equal to any other material that lies on this line. That would be E over rho. So materials like pine, bamboo, age-hardened aluminum, and so on are all very good materials for airplane wings. But a better material would be carbon fiber reinforced polymer with epoxy matrix, or carbon fiber composites. You'll see that they sit way off the line up here, which indicates that their ratio of modulus to density is even higher than these other materials. So sure enough, we make carbon composite aircraft. But here's the problem: carbon composite is very expensive. So if instead we plotted the Young's modulus versus the cost per unit weight, we'd be able to see that a better material, age-hardened wrought aluminum alloys, now stands out as one of the best materials, and carbon fiber composite, which is back here, now is less good than even pine. So if we wanted to make a cheaper airplane, we'd want to make it out of aluminum. And in fact, most of the airplanes in commercial service today are made out of aluminum. Well, let's talk a little bit about composites, since they turn out to be pretty good materials for airplane wings. They're lightweight, they're stiff, and they're very expensive. We can't forget that. There's 4 different kinds of composites. There are particle composites, where you have a matrix material, that's the white, and then you have gray chunks that reinforce the matrix. There are short fiber composites, where you have a white matrix material, and embedded inside that matrix are short glass or carbon fiber composites, or fibers. You have a continuous fiber composite, where you have a white matrix and long fibers that run the entire length of the composite. And you have a laminate. Now, a laminate can be made up of one piece of matrix with some reinforcement in between, kind of like a sandwich, or it can be made up of layers of fiber fabrics, like woven fabrics, in one direction, and then another layer with the fiber going in a different direction. So composites can be very complicated. All composites have one thing in common, and that's what we call anisotropy. Anisotropy is the condition in which the properties vary depending on the direction that you test the property. So for example, the elastic modulus. The elastic modulus of this continuous fiber composite is not the same in this direction, the longitudinal direction, or along the fibers, as it is against the fibers. We'll look more at that in a moment. So what are some types of composites? There are 3 broad categories of composites: polymer matrix composites, metal matrix composites, and ceramic matrix composites. Polymer matrix composites all have polymers as the material that holds the fibers together. So some examples include Kevlar reinforced polymers, carbon fiber reinforced polymers, and glass fiber reinforced polyester, which is also known as fiberglass. There are also metal matrix composites. Metal matrix such as titanium matrix with ceramic fibers that run through the entire length of the titanium component, and also aluminum, the white material over here in the right picture, with chunks of silicon carbide for reinforcement. The fiber reinforced titanium composites are used for aircraft components because they provide very high strength at high temperatures. The aluminum with silicon carbide is used for aluminum pistons and connecting rods in engines and car engines. One of the problems with both of these composites is anisotropy. The properties in the direction of the fibers here are going to be very different than the properties out of plane of the fiber. Likewise, you can see that the chunks clump together or agglomerate. That means that the modulus of the material where it's just pure white, or the pure aluminum, is going to be much different than the elastic modulus over here, where I have lots of chunks of ceramic reinforcement. And lastly, we have ceramic matrix composites. So here's some pictures of actual components made out of ceramic matrix composites. Now, ceramic matrix composites are designed not so much to make the material stiffer, because after all, we've got ceramic fibers inside ceramic material. What the material is there for is to try to stop cracks from growing through the matrix. So as you can see, if I had just a ceramic material, it would be very brittle and cracks would travel through it very easily. But by putting the fibers in place, the fibers actually attract the cracks to them and cause the crack to travel around the outside of the fiber, absorbing the energy of the crack. This slows down or stops the cracks altogether and makes the material that much tougher. So a while ago we mentioned that anisotropy means that the modulus of the fibers in the longitudinal direction or along the length of the fibers would be very different than the modulus in the transverse direction or against or out of plane of the fibers. And that's very true. In fact, we have two entirely different equations for calculating the elastic modulus. Now before we get to that, let me remind you of something very important. If I take the volume fraction, in other words, what percentage of the volume of the composite is made up of fibers, and I add that to the volume fraction for the matrix, those two numbers should add up to 1. There's one total volume fraction. Keep that in mind, because in a problem you might be given the volume fraction of the fibers and not given the volume fraction of the matrix, but using this equation you can always figure out the other property, the other value. Here's the equation for calculating the elastic modulus in the longitudinal direction. So this is the composite modulus, E sub c, in the longitudinal direction. And it's equal to the volume fraction of the fibers times the elastic modulus of the fibers plus the volume fraction of the matrix times the elastic modulus of the matrix. It's a very simple formula, and it actually has a name called the rule of mixtures. In the transverse loading condition, where the stress is perpendicular to the fibers, we get a very different equation. Here, the composite modulus in the transverse direction is equal to the elastic modulus of the matrix times the elastic modulus of the fibers divided by the elastic modulus of the fibers times the volume fraction of the matrix plus the elastic modulus of the matrix times the volume fraction of the fibers. This is not a mistake. This is the modulus of the matrix times the volume fraction of the fibers, and vice versa over here. If we calculate these two values for the same composite, what we find out is that the composite modulus in the longitudinal direction is always higher than the composite modulus in the transverse direction. And that makes sense. If I pull on the composite along the fibers can resist this deformation and therefore make the material stiffer. But here, when I'm pulling transverse to the fibers, the fibers aren't supporting the load, and therefore the matrix material has to support the load, and so the elastic modulus is much lower. We can see this by taking a Kevlar fiber reinforced epoxy and adding different amounts of Kevlar to the epoxy. What we see is that the Young's modulus goes up as I add more and more Kevlar to the material. There is a trade-off though. As I add more Kevlar to the epoxy, the density of the material actually goes up. So while we might make a stiffer composite by adding 70% Kevlar to epoxy, I also make a heavier composite. Mother Nature always has trade-offs like that for us. So let's go back to this idea of anisotropy. What can we do about it to try to minimize its effects? Because oftentimes in design we want to make sure that we either know the properties in all directions or we eliminate anisotropy and we know that the properties are all the same in all directions. There's several different ways of dealing with this. The simplest way is to use what's called a random strand mat. In a random strand mat, you take the fibers and just lay them down in any direction that you can. What that means is that you get the same properties in the X and the Y direction, but the properties will be lower than if all the fibers are going in the same direction. So this leads to poor performance composites, but at least all the properties are the same in all the directions. Another way of dealing with anisotropy is what's called weaving, where I take a bundle of fibers and I weave it through a fabric. Then I pour epoxy or some other resin over the weave in order to make it hard and provide the matrix material for support. This works pretty well for getting you good properties in the X and the Y direction, but what if I'm applying a force at a 45-degree angle to this fabric. It'll deform very easily. So this isn't really isotropic. It's still anisotropic. Its properties are good in the x and y, and maybe even equal, but they're not the same in the xy direction. The last choice is called a laminate, and we already talked about these a little bit. So here's some examples of where I have a unidirectionally reinforced composite with all the fibers running the length of the composite in one direction. This is called the 0 degree orientation. Then I lay down another layer of composite where all the fibers are going 90 degrees to that. And then I can put down another 0 degree, another 0, a 90, and another 0. So if I stack all these together, what I get is a composite that's very stiff in the 0 degree orientation, or the x direction, and very stiff in the 90 degree direction, or the y direction. But again, it's not going to be stiff if I were to apply a stress at, say, 45 degrees to this composite. I can deal with that problem by simply laying down layers of fibers that are at angles. So here again is a 0 degree ply. Below that is a ply with fibers at 60 degrees. Below that is a ply with fibers at minus 60 degrees, and so on.